discussed several examples of connected sets, and then the term domain means it is open as well as connected. Okay. So curve is a connected set. If you take a curve, it's a connected set, but it's not open. So this is not a domain. Whereas if you take, so this is not a domain. Whereas if you take disk, then open unit disk may be, then this is domain. Okay, open unit disk or the whole of complex plane, the domain. In some sense, these are two typical types of domains. I will tell you in what sense, but then these two domains are important, the whole of complex plane or the open unit disk. But at present we want a set to be both open and connected, then any such set will do for the domain of definition of an analytic function. Okay. Now before we come to the definition of analytic functions, let us see proposition 6.1, which states an important property of the domain. So let us consider this proposition 6.1. Can you see proposition 6.1, which states that in a domain D, any two points can be joined by a polygonal path, that is a path consisting of finitely many line segments. So see this domain, for example. So if I take this point and this point, now this is not just connected, it is open and connected, remember. So I can join any two points by line segments. So here I can draw just even one line segment. But if I have a set like this, and I want to join this point with this point, then maybe I have to first go like this, then come here, then go to this point and then join this point. So this polygonal path, okay, this is polygonal path, that is path consisting of straight lines. Similarly, if I draw annulus, if I take this point and this point, let me draw this straight line first and maybe this straight line. I can join this point and this point by finitely many straight lines by using a path which consists of finitely many straight line segments. Now a crucial point is that you may choose this point, crucial in the sense it is convenient, that any such path, the line segments can be chosen to be either horizontal or vertical. So suppose again, if we see geometrically, so suppose if you have this particular set, okay, and if I take this point and this point, then I may go horizontal, then vertical, horizontal and vertical. So now this type of path here and this path, what is difference? This is also polygonal, this is also polygonal, but I am saying that now I have chosen the line segments in the polygonal path to be either horizontal or vertical. So this is vertical, this is horizontal, vertical. So if you consider a domain, then this is always possible. If you consider a domain, it is always possible to choose a path which is polygonal in the first place, that you can always join by path consisting of straight line segments, and further you can also choose these line segments to be either vertical or horizontal. So perhaps you want to try for annulus, one point is here, you may take this, So this is your path, which consists of horizontal and vertical line segments. Even if you take smaller annulus, this is possible. Like that. You can always go vertical and horizontal and join any 2 points if your set is a domain, that is, it is open connected set. Remember, if the set is just connected, then it may not be possible. For example, if you take this curve, okay, and if I take these 2 points, now can I join this first of all by using straight line? Forget about horizontal or vertical. I cannot join, because if I take other point, then this straight line will not lie on the curve again. So here the openness of the set is coming into picture. The facility we have is that the sets under consideration are open and also they are connected. So therefore we are putting both these conditions together, that the domain of definition should be both open and domain of definition should be both open and connected. And then this theorem we are going to use later on, this proposition 6.1, that any 2 points of a domain can be joined by a polygonal path consisting of line segments which are either horizontal or vertical. This will simplify some proofs. The choice of the line segments to be vertical or horizontal will simplify the proofs to some extent. There is nothing much important about that, but then this is just a matter of convenience. Now let us come to definition of analytic function. So you have these notes in front of you, and this is perhaps the most important definition in this course. We have already defined differentiable functions, differentiability at a point. So we have defined differentiability of a complex valued function of a complex variable at a point z0. Now analyticity is typically differentiability in an open set. So it is not just at a point. You require to have, or you demand differentiability at every point in a certain open set. So what is underlying difference in the words differentiable and analytic? So differentiable at a point means at that point only we are talking about only that point. And f of z0 plus h minus f of z0 upon h, limit as h tending to 0 exists, then it is differentiable at that point. What happens in the neighborhood of that point is not important when we are just saying that the function is differentiable at that point. Whereas if we want to say that function is analytic at a point, then it is not just sufficient that function is differentiable at that point, it has to be differentiable, but then also we want a neighborhood of that point such that function is differentiable at every point of that neighborhood. So analyticity is a notion of differentiability in an open set. Okay. So let us see the definition now. So we start with open set S. So S open and f from S to C be a function where S open set in C. So this is complex valued function of a complex variable defined on an open set. Later on we will take this to be domain also as and when required, but at present the definition, for the definition of analytic function, I take S to be open set, and f is said to be analytic in S if f is differentiable at every point in S. So, f is analytic in S means f is differentiable at every point f is differentiable at every point of S. Let me immediately give an example which anyways will come later, which underlines the distinction between differentiability at a point and the analyticity. So, if you consider the function fz equal to mod z square, suppose mod z square, and consider z naught equal to 0. So, I am considering at point 0 the behavior of this function with reference to differentiability. Now, let me write here what is limit of f of z naught plus h minus fz naught upon h as h tends to 0. This is equal to what? Now, z naught plus h is, z naught is 0. So, f of h, but f of h is mod h square. So, limit as h tends to 0 mod h square minus f of z naught is 0 upon h, but mod h square is h bar. This h will get cancelled and the limit will be 0. So, limit of f of z naught plus h minus fz naught upon h as h tends to 0 exists. So, we can say what? F is differentiable at 0. So, this function is differentiable at 0. So, f is differentiable at 0. Clear? Because I have shown that if you take z naught equal to h, limit of f of z naught plus h minus fz naught upon h exists. Now, let me check differentiability at other points. This fz is mod z square, which is actually x square plus y square. So, if I look upon this as uxy plus I times vxy, then this uxy is x square plus y square and vxy is 0. So, this is x square plus y square, but this is real function. So, this I times 0. So, vxy is 0. Now, what is dou by u by dou by x? Dou by u by dou by x is 2x. Dou by u by dou by y is 2y. And dou by u by dou by x, I want dou by v by dou by y for differentiability. But v is 0. So, I want 2x equal to 0. Dou by u by dou by y, I want minus dou by v by dou by x. So, 2y equal to also I want 0. So, Cauchy-Riemann equations are satisfied only at point 0, 0. You observe this, are satisfied only at 0, 0. So, f is not differentiable at any other point. Therefore, f is not differentiable at any point except 0, because that is our necessary and sufficient condition, that is the function should be differentiable, which they are x square plus y square and 0, u and v, and satisfy Cauchy-Riemann equations. So, and Cauchy-Riemann equations is necessary condition for differentiability. That is, if at certain point Cauchy-Riemann equations are not satisfied, then at that point, that corresponding complex point, function is not differentiable. So, other than 0, 0, at no point Cauchy-Riemann equations are satisfied. That means f is not differentiable at any point except 0. So, see here now geometrically, that is at this point function is differentiable, we have proved. But at no other point it is differentiable. So, what can you say about analyticity of this function? See, then the next part of the definition you must read there, that further we say that a function is analytic at a point z0 if there exists a neighborhood delta such that f is analytic at every point of n delta z0. So, if we want to say that it is analytic at this point, we need some neighborhood however small such that every point of that neighborhood the function should be differentiable. But this is not differentiable at any other point, it is only differentiable at 0. So, this is not analytic anywhere. Remember, this is differentiable at 0, but not differentiable at 0, because for not analytic at 0, it is differentiable at 0, but not analytic at 0. Why? Because to be analytic at 0, we must get a neighborhood such that at every point of that neighborhood function should be differentiable, which is not true here. So, f is, so what shall I write? This f is differentiable at 0, but not analytic at any point. Not analytic anywhere. So, this is difference between analyticity and differentiability. Analyticity typically is differentiability in an open set. You need a neighborhood of that, or your domain of definition is open, then you say that function is analytic on that set, means at every point of that set function is differentiable, but every point of that has a neighborhood because this set is open. So, this differentiability in the neighborhood of every point will be automatically satisfied. I mean, in fact, analyticity demands that every point in an open set the function should be differentiable. So, read again that function is said to be analytic in S if it is differentiable at every point of S and S is open, okay. The function which is analytic everywhere, so function which is analytic at every point of the complex plane will be called entire function, okay. So, this is a very special category of analytic functions. So, functions analytic everywhere in C are called entire. Can you immediately think of an example? Polynomial. Because polynomial is differentiable everywhere in the complex plane. Complex plane itself is an open set. So on the whole plane, which is an open set, polynomial is differentiable at every point. Therefore, on the open set C, any polynomial is analytic. That means it is analytic in the entire complex plane. It's called entire function. So this is one important example of an entire function. At present, our stock of examples is restricted in the sense that the functions that we learned in calculus, real variable, which are differentiable everywhere in the real sense, that is suppose exponential function e to the power x. At every real number x it is differentiable and derivative of e to the power x is e to the power x. Sin x differentiable everywhere, derivative is cos x. Similarly, logarithmic function, wherever it is defined it is differentiable. Inverse trigonometric functions. So many other type of functions other than polynomial functions we learned in calculus, which were differentiable everywhere. But for a complex variable, we have not yet defined exponential function, trigonometric function, inverse trigonometric, logarithmic. These functions we have not yet defined. Therefore, our stock of examples is restricted, but then very soon, maybe a couple of lectures time, we will introduce other functions like this, exponential, trigonometric and so on, and then discuss the analyticity of these functions as well. And you will come to know that the exponential function, trigonometric function, they turn out to be analytic everywhere. They are also entire functions. Okay. So our collection of entire functions will grow as we define more elementary functions. But for the time being, it is this example that we can think of. It's an entire function. Now let's see, as it is given in your notes, how we translate our theorem about differentiability, necessary and sufficient condition for differentiability, to necessary and sufficient condition for analyticity. Okay. So let us see the necessary and sufficient condition for analyticity now. Okay. So if you remember, if fz, so now again the setup is S is open set, so this is open, okay, and F analytic, okay, and we want to find necessary and sufficient conditions in terms of uxy and vxy. So suppose these are real and imaginary parts of F. Let us consider in terms of points now. Suppose this is Z0. Okay. F is analytic in S means it is differentiable at Z0. In fact, this set is open and F is differentiable at every point. That is what analyticity means. Yes, last time we saw that differentiability of f at point z0 is equivalent to differentiability of these two functions plus a requirement that these two satisfy Cauchy-Riemann equations. Do you understand this? This function is differentiable at z0 means these two functions are differentiable at x0 y0 if z0 is x0 plus I times y0, and further these two satisfy Cauchy-Riemann equations at that point. Now analyticity means differentiability at every point. So at every point this must happen. Whatever we demanded for differentiability at a point, we want that for every point because analytic means differentiable at every point. Do you understand? So same theorem will reappear, but we want that for every point. So what will happen? F is analytic. So F is analytic in S if and only if. What will happen? Now this statement means f is differentiable at every point, and okay, this means this f is differentiable at every point in S, but that differentiability at a point is equivalent to what? These two being differentiable. So if and only if u, v are differentiable in S, and satisfy Cauchy-Riemann equations at every point in S. I have written the same condition that I wrote last time, except last time the condition was written at a point, whereas today I have introduced analytic function, that means differentiability in an open set. So therefore differentiability at every point, I have translated that condition, the necessary and sufficient condition for differentiability at all points. That means this u and v are now required to be differentiable throughout S rather than just x0 y0, and they should satisfy Cauchy-Riemann equations at all points. So any point u and v are differentiable and satisfy Cauchy-Riemann equation, then at every point by last time's theorem f is differentiable, but that exactly means that f is analytic. And conversely, if f is analytic, then it is differentiable everywhere. So any point z0 you take, it is differentiable. So at that point these two functions are differentiable and satisfy Cauchy-Riemann equations. So this will happen at every point. So this necessary and sufficient condition for analyticity we get. So read this again. Maybe it is there in front of you as theorem 6.2. It is there, say theorem 6.2. So read that. Fz equal to uxy plus ivxy be function defined on an open set S. Remember that. That is very important. Then Fz is analytic in S if and only if uxy and vxy are differentiable at every point of S and satisfy Cauchy-Riemann equations at every point of S. Then suppose u and v have continuous first order partial derivatives. See this, u and v are continuous, partial derivatives of u and v are continuous. So remember, this is fz, uxy plus ivxy. Now if dabba u by dabba x, dabba u by dabba y, dabba v by dabba x and dabba v by dabba y, these four partial derivatives all exist and continuous, suppose are continuous in S, that is throughout S. So at every point these first order partial derivatives are continuous. Now you remember that you have done a theorem in several variable calculus that if the first order partial derivatives are continuous, then the functions are differentiable. That is mean these two are continuous, dA by u by dA by x and dA by u by dA by y. These two are continuous, then the function is differentiable. Now these two are continuous throughout S means this u is differentiable in S. Further, dA by v by dA by x and dA by v by dA by y are continuous in S means v is also differentiable in S. So continuity of first order partial derivative is a stronger condition. In fact, that is sufficient to guarantee the differentiability. So this actually implies that u and v are differentiable in S. And further, if Cauchy-Riemann equations hold, what will happen? Further, if dA by u by dA by x equal to dA by v by dA by y and dA by u by dA by y is minus dA by v by dA by x. So they are continuous and satisfy Cauchy-Riemann equations. But they are continuous, therefore they are differentiable. First order partial derivatives are continuous, therefore u and v are differentiable. And they satisfy Cauchy-Riemann equations. Now see here, if the functions are differentiable and satisfy Cauchy-Riemann equations, then what happens? F is analytic. So F is analytic. So this implies that F is analytic. Now not only F becomes analytic, what happens you see that if F dash Z, we have written at every point the expression for the F dash Z, that is dA by u by dA by x plus I times dA by v by dA by x, and this dA by u by dA by x you can replace by dA by v by dA by y minus I times dA by u by dA by y, because dA by u by dA by x equal to dA by v by dA by y, and dA by v by dA by x is minus dA by u by dA by y. So once these first order partial derivatives are continuous and Cauchy-Riemann equations are satisfied, we get that u and v are differentiable and Cauchy-Riemann equations hold, therefore F is analytic. Once F is analytic, we already know the expression for the derivative. Now by our theorem on continuity, if this function is continuous and this function is continuous, then so is this. So now the continuity of F dash, follows from the continuity of dA by u by dA by x and dA by v by dA by x itself only, suppose. Or if I write dA by v by dA by x and here minus dA by u by dA by y, then only from the continuity of dA by u by dA by x and dA by u by dA by y it will follow that F dash is continuous. So these two are continuous, any expression you may take, these two are continuous, all four are given to be continuous. So F dash becomes continuous. Do you remember our theorem on continuity? If real and imaginary parts are continuous, then the function is continuous. We define only F. So now these two are continuous, therefore F is continuous. So in fact F dash is continuous. So not only F dash exists at every point, that is F is analytic, not only this, but F dash turns out to be continuous. Okay. Remember that F dash may exist just at one point, but it may not exist in the neighborhood of that point, like here in case of mod z square. Then F dash is not even defined at other points. So we cannot talk about continuity of F dash at point z naught. For talking continuity of F dash at point z naught, F dash has to be defined in the neighborhood of z naught. Now analyticity at least allows us to talk about the existence of the function F dash in the neighborhood of z naught. So we can at least talk about the continuity of F dash at z naught. And in fact that is guaranteed if what? If we assume that the first order partial derivatives are continuous. So remember, this is a strong condition than just analyticity. Just analyticity is what? u and v are differentiable. And if we assume that first order partial derivatives are continuous, then that will definitely guarantee analyticity. Of course, we need Cauchy-Riemann equations, but then first order partial derivatives are continuous and Cauchy-Riemann equations are satisfied, then that not only guarantees that f is analytic, but in fact guarantees that f dash is continuous. And converse is of course obvious, that suppose if f is analytic, okay, so here we have seen that suppose if this, then that happens this, and therefore f dash is continuous in S. The converse is obvious in fact, because suppose f is analytic, just observe the argument. In fact, it is given to you there, that is say maybe next page, theorem 6.2, this proof of the theorem 6.3, that is f is, but you can observe here, you don't have to look at the notes even. So f is analytic in S, suppose, then what happens? F dash is naturally this, because f is analytic, then u and v are differentiable and satisfy Cauchy-Riemann equation, that is given. So f dash you can write like this, da by u by da by x plus I times da by v by da by x, and also you can write like this. Now this, both the expressions we need now, because f dash is equal to this. Now f dash is given to be continuous. F is analytic and f dash is continuous, that is our assumption now. If f dash is continuous, then this function is continuous. Again refer to our theorem on continuity. So this is continuous if and only if real and imaginary parts are continuous. And it has both this type of expression. So this is continuous, this is continuous, this is continuous, and this is also continuous. That means all first order partial derivatives are continuous. So the continuity of f dash is equivalent to continuity of the first order partial derivatives along with the Cauchy-Riemann equations. So now listen to this statement carefully. Analyticity of f is equivalent to differentiability of u and v and Cauchy-Riemann equations. One statement which I have written here. Analytic in S if and only if u and v are differentiable and satisfy Cauchy-Riemann equations. Whereas analyticity of f plus continuity of f dash f dash continuous is equivalent to what? Continuity of the first order partial derivatives and Cauchy-Riemann equations. So let me write that theorem here so that you will be able to compare the two statements and give some thought to both the statements. So I am writing now the other statement here, and let me check whether the camera captures both the statements. Let us see. I have written one statement here and I want students to read both the statements. I am writing one more statement here now. Okay. So f is analytic in S and f dash is continuous in S if and only if da by u by da by x, da by u by da by y, da by v by da by x, da by v by da by y are continuous in S and satisfy Cauchy-Riemann equations and satisfy Cauchy-Riemann equations in S. In S means at every point in S. At now read both the statements carefully. This is the setup and we have these two statements. F is defined on an open set, complex valued. Fz is uxy plus ivxy. Now this is necessary and sufficient condition for analyticity of F in S, and this is necessary and sufficient condition for analytic, and F dash is continuous. Okay. Read both. Yes, good job. Here the condition is only analyticity, and here we have only differentiability of u and v. Cauchy-Riemann equations are common. That is the bridge actually, the real and complex differentiability. So that has to be there. What are differences you see here? So it is analytic, and f dash continuous you want, then you want these partial derivatives to be continuous. All right. Though I have written these two statements and I have said that continuity of f dash, this is condition, and analyticity of f, these are condition, and so on. A theorem in complex analysis, which is very important, and typically in the complex domain will later on tell you that analytic in S will actually imply that f dash, that it is actually f dash is also, f dash not only exists, f dash is differentiable. So that there is something amazing that happens, that if you have analytic function in S, then this will automatically follow without anything additional actually. So the assumption of f dash continuous is as such superfluous. But at present, just to understand what is going on, I have written these two statements, these two separate statements. Is this clear? Later on we will see, for that we may need some more theory, but then it will follow that if f is analytic, then I don't have to again say that f dash is continuous and all that. It will automatically follow. In fact, f dash will be differentiable. So f dash will be also continuous naturally. And because f dash will be differentiable, f double dash will be differentiable at every point in S. So f dash will be analytic. So f analytic in S implies f dash analytic in S. Isn't it very surprising to you? Because this doesn't happen in real case. Real case in the sense that in the calculus it doesn't happen. We have functions which are differentiable once, but they are not differentiable twice in a certain set. Here the notion of analyticity gives us that if f is analytic on an open set S, then f dash will be analytic. So f dash will be differentiable at every point. So f dash will be naturally continuous. So this will be anyway superfluous. And f double dash will exist, f double dash will be analytic by the same argument. Once analyticity of f implies analyticity of f dash, analyticity of f dash will imply analyticity of f double dash, and then f will be infinitely differentiable. So analytic function on a domain, analytic function on an open set will automatically become infinitely differentiable. But that will follow after we do some theory. And therefore, just to give you some idea of what implies what, I have written two statements which are separate, but actually as such the existence of partial derivatives, okay, the differentiability of u and v, and if they further satisfy Cauchy-Riemann equations, that will be sufficient to guarantee that f is analytic and f dash is continuous. So this itself will guarantee the continuity of f dash. Okay. All right. So in this connection, okay, whatever at a point what happens, I have given in the bracket. So now a standard theorem about the sum, product, linear combination, all that is written on the next page. So theorem 6.4 deals with analyticity of sum and all that, but now these two theorems will use for giving examples of analytic functions or discussing the aspects which are related to u and v especially. So can you write the proof of the theorem 6.4 which is stated here, and you read that the sum, product, linear combination and composition of functions analytic in a domain are analytic. What is analytic anyways? Is differentiable at every point, and we have proved corresponding theorem about differentiability, that is f is differentiable, g is differentiable, f plus g is differentiable, f into g is differentiable, scalar multiple is differentiable, therefore linear combination will be differentiable, composition of differentiable function is differentiable. In fact, we have proved the chain rule also. Now analytic means on an open set it is differentiable everywhere. So all this will happen at every point in an open set. So if f and g are analytic on set S where S is open, I don't have to say this all the time. Remember, if functions are defined on a set, it will be assumed to be an open set. So if f and g are analytic, that means f and g both are differentiable at all points of S. Then f plus g will be differentiable, fg will be differentiable, alpha f plus beta g will be differentiable, f of g, that is composition. For composition you need to have that, again the domains are adjusted so that range of f is contained in domain of g and so on, but wherever the composition is defined, composition is differentiable, because whatever we have proved for differentiable at a point is valid for analytic functions, because that is nothing but differentiability but applied at every point. So the sum, product, linear combination, composition of functions analytic in a domain are analytic. F by g is analytic if f and g are analytic and g dash non-zero. Okay, so this now comes the examples of analytic functions. You see examples there. I have already discussed first two examples, that is polynomial is the entire function and a rational function is analytic in complement of a finite set consisting of zeros of the polynomial in the denominator. So if you have f by g, that is p z by qz, that is a rational function rz, then except for the zeros of the denominator, okay, so q dash, so wherever this q is 0, r is not defined at, okay, and then q dash z is non-zero, then you can find this should be qz actually, where g is non-zero. This wherever q is non-zero, r is differentiable wherever q is non-zero. So zeros of the denominator you have to give on. and then mod z square I just now discussed with you. So it is not differentiable at any point except 0. So you can read that. Next page. Example 2 is mod z square, which I have already discussed, that it is not analytic anywhere. It is differentiable at 0, but as it is not differentiable anywhere else in the complex plane, it is not analytic anywhere, because we cannot say that it is analytic at 0, because for analyticity at 0 I want a neighborhood of 0 such that at every point of that neighborhood f is differentiable, but it is differentiable only at 0, so it is not analytic anywhere. See the third example. Here f is defined by using real and imaginary parts. So fz is defined as e raised to minus y sin x minus I times e raised to minus y cos x. So this is uxy, okay. So uxy is what? The function is defined in terms of real and imaginary parts. So this is sin x, and vxy is equal to what? Minus e raised to minus y cos x. Now we know necessary and sufficient conditions for analyticity. That means first of all we have to check Cauchy-Riemann equations. Wherever Cauchy-Riemann equations are not satisfied, there is no question of differentiability. So let us first of all find first order partial derivatives. So what is dA by u by dA by x? So this is sin x, so e raised to minus y cos x. And what is dA by v by dA by y? This is v. So with respect to y means this will become plus. So e raised to minus y cos x. Clear? So dA by u by dA by x equal to dA by v by dA by y. I have not specified the domain of f, but then f is assumed to be from C to C. So this I am writing like this means they are satisfied everywhere. There is no exception. You may take any x and y, they are satisfied everywhere. This equation is satisfied. Now let us find dA by u by dA by y. So this is u, dA by u by dA by y means minus e raised to minus y sin x, and dA by v by dA by x is dA by v by dA by x is minus minus plus it will become e raised to minus y cos x. So dA by u by dA by y is minus dA by v by dA by x. So Cauchy-Riemann equations hold. Cauchy-Riemann equations are satisfied. U and V are differentiable. This is exponential function, this is sin x. As real functions we already know that these are differentiable functions. In fact, the first order partial derivatives are also continuous, alright. So U, V are differentiable. U, V are differentiable, and Cauchy-Riemann equations are satisfied. Therefore, what will happen? By our sufficient condition, and this happens everywhere in C. So everywhere f is analytic. Therefore, f is analytic everywhere in C. That is, f is the entire function. F is an entire function. See example number 4 now. Next example that I have written there in the notes. Fz equal to, again it is defined in terms of uxy and vxy. So Fz is 2xy plus I times x square minus y square. Whenever a function is given to you like this in terms of u and v, you first of all write uv, write dabba u by dabba x, dabba u by first order partial derivatives, and check Cauchy-Riemann equations. Okay. That will first of all eliminate the points where it cannot be differentiable, because at certain point Cauchy-Riemann equations are not satisfied, then f cannot be differentiable. So let us find uv. So what is uxy? It is real part, that is 2xy. Vxy is what? X square minus y square. So what is dabba u by dabba x? Dabba u by dabba x is equal to 2y. Dabba v by dabba y, dabba v by dabba y is minus 2y. But we want dabba u by dabba x equal to dabba v by dabba y. So these two we want equal for Cauchy-Riemann equations. But then that will force 2y equal to minus 2y. That means y is equal to 0. Okay. Let us write dabba u by dabba y. What is dabba u by dabba y? That is 2x. And dabba v by dabba x, that is also 2x. But we want dabba u by dabba y equal to minus dabba v by dabba x. So 2x equal to minus 2x, that means x equal to 0. So Cauchy-Riemann equations are satisfied only at 0, 0. Is it clear? Because Cauchy-Riemann equations force that 2y equal to minus 2y, so y must be 0. 2x equal to minus 2x, so x must be 0. So only at x equal to 0, y equal to 0, that only one point the Cauchy-Riemann equations hold. So at all other points f is non-differentiable. So points where Cauchy-Riemann equations are not satisfied, function cannot be differentiable. Okay. So f is not differentiable. What is f? F is this complex function, is not differentiable at any point except 0, 0. And what happens at 0, 0? Cauchy-Riemann equations hold, and these functions are polynomial. So these u and v are differentiable functions, and Cauchy-Riemann equations are satisfied at 0, 0. So at 0, 0, our local condition is satisfied. That is, at a point, if Cauchy-Riemann equations hold and functions are differentiable, then f is differentiable. Okay. So at 0, 0, u, v are differentiable. In fact, u, v are differentiable everywhere. They are polynomial functions. At v, u, v are differentiable. And Cauchy-Riemann equations are satisfied. Thus, f is differentiable at 0. So it is not differentiable at any other point, but differentiable at 0. So what can you say? It is nowhere analytic. It is differentiable at 0, but it cannot be differentiable at any other point. So you cannot find a neighborhood such that at points of that neighborhood f is differentiable. It is only differentiable here. So can you say that it is analytic at that point? No, because analytic at that point would amount to what? There is at least some neighborhood, however small, such that f is differentiable at every point, which is not true. So f is nowhere analytic. It is nowhere analytic. Okay, so the time is over, but I suggest that you go through the remaining parts of the notes. I have given some more examples and then some direct implications of the Cauchy-Riemann equations are discussed. Anyway, those implications we will do next time. Remember the statements which we have done in case of real variable. For example, f dash equal to 0 in an open interval, then f is constant. Like that we want to derive certain statements for the complex functions. So those I have written in the next theorem as constancy in the domain. That is, under certain conditions we always get that the function is constant. So that is, for example, f dash equal to 0, f is real, or mod f is constant, or f z bar both analytic, and so on. So we shall continue with the discussion of analytic functions next time, and derive certain consequences of the definition as well as consequences of the Cauchy-Riemann equations, because if f is analytic